Welcome back. Today, we're diving straight into the deep end of vision language models. If you're an ML engineer or researcher, basically anyone trying to keep up, the field's kind of split, right? You've got this choice. Go modular or go native.
Exactly. And for a while now, modular VLMs have been king. The ones where you take a pre-trained vision encoder, stick a projector in the middle, and bolt on a big LLM.
They get the job done, sure, but wow, they can be beasts to manage. Complex infrastructure, huge data needs. We're talking billions of examples sometimes just to get the parts talking nicely.
Yeah, and that complexity, it really slows down research. Then you have the other dream, the native VLM, one unified model. Elegant, right?
Sounds great on paper.
But history shows they've been, well, tricky, unstable training, and worse, they often mess up the LLM's language skills trying to integrate vision.
Okay, but that's where today's paper comes in. From pixels to words, it introduces NEO, a new family of native VLMs. And here's the quick summary, the 1-minute insight you need.
Right, so NEO seems to have cracked that stability issue. They use this new idea, a native VLM primitive. It basically handles the encoding, the alignment, the reasoning, all inside one dense model. And here's the kicker. It learns really strong visual understanding from scratch using surprisingly little data, just 390 million image-text pairs total.
Which is tiny compared to the competition, and NEO is holding its own against top modular models of similar size, models trained on like 6 billion examples or more.
Exactly. It suggests maybe it's not just about throwing data at the problem. Smart architecture might be a more efficient path forward for multimodal AI.
Okay, let's dig into that modular approach first, the standard way, decoupling everything. Why did people go down that complex route with separate encoders and projectors?
Well, honestly, because it worked reliably or reliably enough, you could leverage these powerful pre-trained parts that were already experts, right? The vision encoder, new vision, the LLM, new language.
And the projector was the translator in the middle.
Kind of, yeah. More like a bottleneck trying to compress the visual info into something the LLM could digest. But the cost.
What was the real cost?
Well, first, alignment is painful. Lots of multi-stage training after the main pre-training. And then there's this big issue. Inductive biases.
The model's built-in assumptions from its training.
Exactly. So if your vision encoder was only ever trained on, say, 224 by 224 pixel images, it's got this ingrained habit. It struggles with high-res stuff, different aspect ratios later on. You're constantly fighting the model's past.
Okay, that makes total sense. So people tried native models before Fuyu, EVE, those sorts of things, aiming for that early fusion, merge vision and language sooner. But they hit walls.
They did. Trying to map vision directly into the LLM often destabilized the whole training process, and it led to this thing called linguistic knowledge corruption.
The model forgets English.
Basically, yeah, it gets so focused on integrating the visual stuff that its core language abilities degrade. That instability meant researchers had to use workarounds like distillation training a smaller model using a bigger one, just added more complexity back in.
Right. So NEO's claim is different. They went back to basics, first principles, designing the core transformer block to handle both modalities without these conflicts.
That's the core idea. Build it from the ground up to be multimodal, stable, and efficient without needing those extra complex stages or tricks. The goal is a truly unified system. So to get this unified thing working, NEO needed some fundamental changes right inside the transformer block. 2 big architectural shifts: multi-head native attention MHNA and native ROPE.
Okay, MHNA first. How does one attention mechanism handle both a line of text and a 2D image grid effectively?
Right, so MHNA adapts the standard attention. It actually expands the dimensions for the query Q and key K heads, but specifically for the spatial information, the height H and width W of the image. Language is still the temporal T dimension. This adds maybe about 10% more parameters to the block, giving it the actual capacity to process 2D structure.
Hold on. If you're just adding new parameters for vision into a finely tuned LLM, wouldn't that cause chaos? You mentioned zero initialization.
Yes, that's the secret sauce for stability. It's crucial. The linear weights for the key, K, that handle those new H and W channels, they're initialized to 0.
0. So at the start.
At the start, the LLM core essentially ignores those visual channels because the connection strength is 0. It keeps its language abilities perfectly intact. Then, as training progresses, those weights gradually learn and increase.
So the visual capability ramps up slowly, progressively, without shocking the system. Very clever, like easing it in.
Precisely. And this careful integration allows for another smart trick: mixed attention.
Mixed. How so?
Text tokens use the standard causal attention, They only look backwards, which you need for generating text step by step. But the image tokens, they use full bidirectional attention.
Meaning every image patch token can look at every other image patch token.
Exactly. Just like a dedicated vision encoder would, it's vital for understanding the whole image, seeing how all the parts relate spatially.
Okay, makes sense. Now, the second piece. Native ROPE. Positional encoding, telling the model where things are, gets messy with vision and language together because the scales are so different, right?
Totally different scales. It's a huge problem. Think about it. LLMs deal with sequences, maybe up to 1 million tokens long. That's the temporal range. 166 others are. Their spatial range, height or width, is maybe a few hundred pixels or patches, 102 twos.
Trying to use the same positioning system for both.
It just doesn't map well. Standard ROPE approaches conflict. You end up confusing the model about relative positions in text versus images.
So native ROPE fixes this how? Decoupling.
Exactly. It fully decouples the position information, both the channels and the frequencies across all 3 dimensions. Temporal T for text, height H, and width W for images.
How does it decouple the frequencies?
It assigns different base frequencies. For the T-dimension text, it uses a big frequency, like $1 times 166, which helps capture long-range dependencies in language. But for H and W, the image dimensions, it uses a much smaller base frequency, $1 times 144. This tells the model to focus more on local dependencies, spatial relationships nearby, which is critical for vision.
Got it. Tailoring the GPS to the type of data. And what about indexing for images?
Also smart. For image inputs, the H and W indices start fresh from new algo independently, but they maintain the same relative positioning. This helps the model understand spatial structure consistently, even when comparing multiple images. It's really built to handle the geometry clash from the start.
Okay, the architecture sounds solid. But the big hurdle for native VLMs has always been training them efficiently, especially without wrecking the LLM core when you introduce vision from scratch. NEO uses a partitioned backbone.
Yeah, they have this clever setup during the initial training phases. So input comes in through a simple patch embedding layer, PLL, just a couple of convolutions to turn image patches into tokens, and the standard word embedding layer, well, L for text. Then the main model, the backbone, is temporarily split into 2 parts.
2 sections.
Right. The first few layers, let's call them LOR1, act as the pre-buffer. Its job is the initial encoding and sort of pre-aligning the vision and text. The rest of the layers, pre-LLM, form the post-LLM. This part does the heavy lifting for final alignment and reasoning, and crucially, it starts with the weights from a strong base LLM, like Qwen 3.
How deep is the pre-buffer usually?
It depends on the model size. For their 9B model, it was only the first 6 layers. For the 2.2B, it was 12.
So the pre-buffer is like the crumple zone, absorbing the initial impact of the visual data.
That's a really good analogy, yeah. And this structure enables their 3-stage training process, which is key to the whole stability thing. Stage 1 is pre-training. They use about 345 million image text pairs. And here's the absolute masterstroke. The weights of the post-LLM, the 2 layers, they are frozen.
It's completely frozen.
Okay, that's the protection mechanism. That's how they avoid corrupting the language part.
Exactly. The LLM core is untouched. Only the image input layer, PEL, that pre-buffer LL1, and the new vision-specific attention weights, those zero initialized QK parts, are actually trained. They're forced to learn basic visual concepts using just next token prediction, but they can't mess up the powerful language model sitting downstream.
So stage 1 is like a safe sandbox for learning basic vision. Then what happens in stage 2?
Stage 2 is mid-training. They bring in about 40 million more diverse examples, things like high-resolution images, data for OCR, object detection tasks, and now they unfreeze everything. The full architecture gets updated.
Because the model has a stable visual foundation from stage 1, precisely. Stage 2 is about strengthening that alignment and building more complex multimodal skills. Then finally, stage 3 is supervised fine-tuning on maybe 4 million high-quality instruction examples. At this point, that conceptual partition between pre-buffer and post-LLM disappears. It becomes one seamless, monolithic backbone that has learned how to automatically distribute the work, encoding, aligning, reasoning across all its layers to follow instructions.
And there's a side benefit here for researchers, right? That pre-buffer module.
Huge benefit. Once trained in stage 1, that pre-buffer becomes a reusable component. Anyone wanting to build a new native VLM on top of a different base LLM can potentially just grab NEO's pre-buffer, significantly cutting down their own training time and cost. It lowers the barrier to entry.
Right, let's get to the bottom line, the results.
Yeah.
Does this elegant architecture, this careful training process, actually pay off against the big modular models?
The results look, well, pretty remarkable, actually. NEO shows really competitive performance at both the 2 billion and 8 billion parameter scales. And remember, we have to stress this point from the paper. It's competing well against established modular systems, things like Qwen2VL, Intern VL 2.5, models that were trained on vastly more data, often over 6 billion pairs.
Compared to NEO's 390 million total, that's less than 10% of the data in some cases?
Something like that, yeah. It really does seem to validate their argument that smart architecture and stable training can be a powerful substitute for just drowning the model in data.
Okay, and how does it stack up against other attempts at native models?
That's also telling. Compared to models like Mono, Intern VL, or Havali, NEO shows significant improvements, especially on benchmarks that really test visual understanding. It suggests their native VLM primitive, the MHNA and native rupee, genuinely overcomes those core modality conflicts that hindered earlier native designs.
The ablation studies seem to back this up strongly too, don't they? Isolating the impact of specific design choices.
Absolutely. They clearly show, for instance, that using their mixed attention consistently beats trying to use just causal attention for everything. It proves that letting the image tokens talk to each other bidirectionally is crucial.
And the positional encoding. Native rupee.
Also a clear win. Decoupling T, H, and W gave them a consistent edge around 0.8% average accuracy gain over simply methods like just using 1D rupee. It proves you really do need to handle those different scales and dimensions properly for effective native fusion.
But it's not perfect yet. The paper mentions limitations, right? Struggling a bit on knowledge-heavy tasks like MMMU or InfoVQA and maybe some OCR tasks.
That's right. And this seems to point back to the training data. The authors themselves suggest that the performance ceiling on those specific tasks is likely due to the size and type of data in their relatively small 390M pre-training corpus, rather than a fundamental flaw in the architecture itself.
So the thinking is the architecture is sound, potentially very scalable from 0.6B up to 8B and beyond, but it just needs more or perhaps more targeted data to excel in those highly specialized areas.
That seems to be the hypothesis, yes. Feed it more knowledge-rich or OCR-focused data, and its performance there should improve significantly, given the solid foundation. So, stepping back, the big picture here with NEO is it's potentially more than just another high-performing VLM. It feels like a validation of the native monolithic approach. It gets rid of the need for separate visual encoders, complex projector modules, distillation, all these things that add complexity to modular systems. The philosophy seems to be design the unified architecture correctly and let the model figure out how to use it efficiently during training.
And the architecture itself might be setting a foundation for more than just static images. The paper hints at this, right? The way it handles T, H, and W.
Exactly. That careful integration of temporal, height, and width dimensions, especially with native rope and mixed attention, sounds almost purpose-built for things like video understanding, which is essentially sequences of spatial grids, or even embodied AI interacting in 3D space.
So the suggestion is that this kind of unified primitive isn't just solving today's VLM problems, but might be the architectural pattern needed for those much harder next-generation multimodal tasks.
It certainly feels like a strong possibility. It's inherently multidimensional in a way that purely text-focused or simple image-text models aren't. It could be a key piece of the puzzle for scaling to richer modalities.
Well, this dive into NEO definitely highlights a fascinating shift towards potentially more efficient and elegant VLM design. And good news for everyone listening who wants to get their hands dirty. The authors plan to release the code, the model weights, the documentation, making it easier for the community to build on this work. So here's something for you to think about. If architectural innovation like NEO's really can reduce the reliance on massive data sets, how might that change the game for smaller research labs or startups competing against the giants with huge data resources? Could ingenuity start to level the playing field a bit more?